So number one, right? So the general idea of relativity, as opposed to specifically Einstein's special relativity, right, means that when we're talking about a measurement, generally we're talking about the measurement as we view it, right, from our own perspective, or the technical term for that is our own frame of reference. Galileo, he came up with the idea, right, that the laws of physics should be the same for all frames of reference. Which are at rest or moving at constant speed. And here's where the key word comes in, relative to each other. So that's where we get the idea of relativity. Historically, it was believed right, that there was a universal or kind of absolute, right, frame of reference from which right, from which all other frames of reference could take their relative measurements. Right, that basically there was this grand universal, there was a point which you could call is the 0 point of the whole universe. Right? It was at rest and everything else was moving relative to it. Because that's the kind of idea that we're used to. You know, if we take measurements in this lab, we consider this lab to be at rest. Right? So if a pen's sitting in a desk in this lab, we say the pen's at rest. But it's not, the Earth's spinning. Right? The Earth is also orbiting the Sun. The Sun is orbiting the centre of our galaxy. Our galaxy is moving through space. So there's all this relative movement. Right? And we just pick the reference frame that we're in to take the measurements. But there was this kind of historical belief that there will be a kind of universal reference frame from which everything else could take its measurements. But this was disproven, basically. at the beginning of the 20th century. So around about the time that Einstein was developing his work, right, there was another experiment done called the Michelson-Morley interferometer experiment, which basically showed that whatever direction you were moving in, right, the speed of light was always the same. Now, that kind of then leads to problems with an absolute frame of reference. Right? If it doesn't matter what speed that you're moving, right, then it kind of does away with that issue of a universal or absolute space, absolute time. Now, am I expecting that you memorise this phrase, Michelson-Morley interferometer? No. It's much more about, I would say, for these learning outcomes, that you would recognise it if somebody was discussing it in a paper.
What did you say this learning outcome?
Okay, number 2. So it says, describe the experimental and theoretical considerations which lead to the conclusion that the speed of light is the same for all observers. So the Michelson-Morley interferometer experiment but at the same time as that was being done, Einstein was developing his thought experiments. And he came up with the idea that if a light source was on a moving train, and that train was, say, moving at half the speed of light towards you, does that mean that the light would be going at half the speed of light towards you? Because that's kind of standard relativity. He said, no, that can't make sense. Because if you take that to an extreme, if the train's coming towards you at the speed of light, then the light isn't moving towards you. Right? It has zero speed. Which doesn't make sense because light can't then exist. Because it's not solid matter. Right? It only exists because it's a wave which is moving, and if you could somehow stop it moving, then it wouldn't exist. Right? Which, what have you done with that energy, basically? All right. So Einstein's thought experiments considered the effect of a light source on a moving train. If the train was travelling at the speed of light, then Newtonian relativity would suggest that the light wasn't moving relative to you. This doesn't make any sense because light has no mass. And can only be considered as moving energy, i.e. a wave. is, so the speed of light number 3. Okay, and basically number 3 says, state that the constancy of the speed of light led Einstein to postulate that space and time for a moving object are changed relative to a stationary observer. Okay, so by considering, and once again this is his thought experiments, so by thinking about these, and this is, remember the one in the tram, where we were talking about looking at a clock and what effect you have, if the speed of the tram was significant compared to the speed of light, then that would affect the time measurement that the person sees. Right? That somebody standing under the clock would see time passing at one rate, where somebody moving away at a significant fraction of the speed of light would see time passing at a different rate. Right? So that was the kind of things that Einstein was able to work out just by thinking about it, basically. So Einstein predicted are not absolute, but change for a reference frame moving relative to another. What I would normally do, remember anyway, is define the formula. I think the key point in this formula though it's probably just worth emphasising that fact. Right? T dash is relative time, right? i.e. right, time measured when observing a different reference frame. So it doesn't matter whether it's consider that your reference frame is moving and the other reference frame is stationary, or you consider your reference frame is stationary and the other one is moving. If you're observing something in a different reference frame, then that's T dash. Right, that's your relative time.
So you would notice it from Earth, but that's in proper time? Like observed from
If you're on Earth, yeah, then that would be proper time. But if you're in a rocket watching something on Earth, then that would be relative time. Okay? A proper time is time measured in the same reference frame. And v is the speed of relative movement. Now, example. The rocket's travelling past Earth at a constant speed, 2.7 times 10 to the power 8 metres per second. The pilot measures the journey as taking 240 minutes. How long did the journey take when measured by an observer on Earth? So first of all, the obvious information we're given in the question, standard problem solving techniques. You're given v, the speed of relative movement. We're also given that the time, now this is proper time, is 240 minutes. It's proper time because it's measured by the pilot measuring the journey, right, of the rocket, so it's in the same reference frame. The speed of light, we know, is 3 times 10 to the power 8. And the question then is asking us the relative time. Right, the time is measured by somebody in a different reference frame. Okay, write out our formula. Remember, that gets you a mark, just writing that out. In this case, this 240 is square root of 1 minus. Now, I could cancel out the times 10 to the power 8 bits at that point. You could put them in and then cancel them out if you want, but I can simply write that as 2.7 over 3. And then it's just a plug into your calculator. And you get 550 minutes in this case. Just a reminder of the formula. Relative length. I'm just kind of abbreviating. What we had the previous time. The spaceship is 500 meters long. what length will it be when measured by a stationary observer while moving at 0.8 c. So quite often that's the way that the speeds are expressed. Right, fractions of the speed of light. So once again, what do we know? We're told L is proper length. We're told that V is 0.8 times c. We know what c is, but in actual fact it doesn't matter in this example. Because now when we substitute in L dash as L, what you get is 0.8 c divided by c. So the c's cancel out.